We've now seen two really important relationships related to net force. The first is that we saw that the net force can be calculated by looking at all of the different forces acting on an object. And typically with that, we would draw an FBD, a free body diagram, to understand all of those different forces, and that helped us to find the total force that way. But we've also seen that net force has to do with Newton's second law. And Newton's second law says that net force also has a direct connection to mass times acceleration. More specifically for our purposes then, that gives us a connection between forces, which we've studied in Unit 2, and some kinematics concepts that we studied in Unit 1. Specifically, now we've linked net force with acceleration. And acceleration we've already seen previously. So what we're going to do in these examples is use some force analysis to help us understand net force, and then see if that can help us to find some kinematics-related stuff, like first acceleration, but also other things if we want to find them as well. So our first example is just a 35 kilogram box being pushed forward with 455 newtons of force, and the box experiencing 402 newtons of frictional force. We want to find its acceleration. So with all of these questions, as you can probably guess from the title of the note, we're going to draw some FBDs to first organize our forces. So if I draw the box, I know that it's got some applied force pushing it forwards, what I'm going to call FA, and it's got some frictional force back in the other direction, what I'm going to call FF, the frictional force. But remember, those aren't the only two forces involved. It's still trying to be pulled down by the force of gravity, and it's not going through the table, which means it must be pushed back up by normal force. More specifically, we can also add little dash marks to those as well, because we know gravity must be equal to normal force in this case. So the only other forces that are really contributing to an overall net force are the applied force and the frictional force. So let's give ourselves some space to work. And as always, start with given and required information. So we know that the applied force is 455 newtons. And for right now, I'm just going to talk about the magnitude of that force. The amount of force is 455 newtons. And we'll look at direction a little bit later on. We also know the frictional force is 402 newtons. We're told that the mass of the box is 35.0 kilograms, so we'll just keep that in mind and see where it could be useful. In the end, though, we're trying to find acceleration. But as we said, if we just know forces involved, the forces on their own don't tell us acceleration. So really what we're going to try and do first is find F net. That's not our long-term goal, but that's something we're going to need to find, and then we can use that information along with Newton's second law to find acceleration. When we actually go to solve these problems, there's a specific way that I would always like you to start off these questions. And it goes like so. In general, net force, and in this case I'm going to use the full vector version of it, I'm going to state that net force, well, it's really just all of the forces added together. We know that it's also equal to mass times acceleration, but net force just means total force. So I find this net force by adding together all of the forces. So I have the force of gravity, I have normal force, frictional force, and applied force. And notice I put vector arrows on all of them, because technically, remember, even though some might be in what we call a negative direction, we really are adding all of those vector forces together. But once we write out this general statement that helps us understand all of the forces involved, we can start to simplify it from there. For example, we already know that the force of gravity is being canceled out by the normal force in this case, because the object is not accelerating up or down at all. And so we can actually completely eliminate those forces. And so in the end, we're going to be left with just frictional force and applied force. In my next step, I'm going to get a little bit tricky in terms of notation. So in my next step, I'm going to include the fact that I've got frictional force and applied force, but I'm going to drop the vector arrows. And I'll show you why. In reality, what's going on is that we've got some negative amount of frictional force, because the frictional force will always be working against whatever direction I've defined as positive. But we're going to be combining that with some positive amount of applied force. Now again, notice that when I wrote those, I just wrote the F's. I didn't write the little vector symbols on top. And that's because I literally just mean the magnitude of each force. So what I'm saying here is that friction will be in the negative direction with that amount of force, with whatever I've called FF. So in this case, 402 newtons. Whereas the applied force will be in a positive direction with that amount of force. So I'm essentially creating vectors, but just indicating to you that we can take the positive or negative version of the magnitude of that force vector. So what does that mean in my next step? Well, that means I have negative 402 newtons of force being added with positive 455 newtons of force. So when I do all of that, I get a positive number. I get positive 53 newtons, which in other words means 53 newtons forwards. So even though we didn't define this from the start, we can include an extra statement that says this direction that we've said to the right will be our positive direction. And then friction works back in the negative direction. So again, going through that process, we start in our very first step by just stating all of our forces combined, and still including the vector arrows on top of them, because we really are adding all of those vectors. But now, in our next step, we're realizing that friction is really a negative force. So if we just put a negative sign in front of its magnitude, and a positive sign in front of the applied force magnitude, that really represents them as vectors, because one is going directly in the negative direction and the other is going directly in the positive direction. Then we sub in the magnitude numbers that we actually know. The friction, of course, has the negative in front because we know it's in the negative direction. And we add that positive, and we got a positive answer. And then if we wanted to actually state this as a final answer, you'd want to state it in the way that I listed below, that it's 53 newtons forwards. But in this case, we can actually just leave it for now as 53 newtons, because we're not quite done yet. Remember, our end goal was to actually find the acceleration. So now if you've run out of room, you may need to extend this onto a separate sheet of paper and just connect it later on. But the idea now is that now we have our net force. And we also know that F net is equal to mass times acceleration. That's not the version of the formula we want, though. We want the fact that acceleration would be our net force divided by our mass. And notice I've left the vector arrows on because I am going to write my values in as a vector. Specifically, I'm going to write that this is positive 53 newtons. That is a vector quantity, and the positive is something that allows me to state the direction along with it. And I'm dividing that by the 35 kilograms. So when we do that, 53 over 35, we get approximately 1.5 when we round to two significant digits. So we get 1.5, and in this case, remember, it's meters per second squared because it's an acceleration. And of course, in your notes, you should also include a therefore statement to say that therefore the box will accelerate at 1.5 meters per second squared. Now, technically, in your therefore statement, it's good to remember that you got a positive answer. So really, what this means is that we got 1.5 meters per second squared in the forwards direction, or that direction we defined as positive in the first place. So this object is accelerating in the direction of its applied force, because that also happens to be the direction of its net force. Our next example then is looking at a hockey puck. And it's been shot along the ice, and we know the coefficient of friction, specifically kinetic friction between the puck and the ice. We know it's kinetic friction because the puck's going to be moving along the ice, but still feeling some amount of friction while it moves. So if that coefficient of friction is that very small value, 0.0060, we once again want to find acceleration of the puck. So this approach is going to be very similar to what we've done so far. We're going to map out all of the forces involved through a free body diagram, use those forces in our net force equation to come up with a net force if we can, and then try and use that net force through Newton's second law to find acceleration. But first things first. So what's important to remember about this question is that we're doing everything after the puck has been shot. So this is all about the puck, but after being shot. So keep that in mind. And that's really important when we go to draw the free body diagram. You could draw it as a dot or a box or really anything you want, but I think I can handle a puck. So I'm going to draw my puck kind of like that. That's my hockey puck. And I know it's on the ice, it's sliding along the ice. And so even though gravity is trying to pull it down, that must mean there's still normal force pushing it back up from the ice. More specifically, we know that gravity and normal force are equal to one another and balancing one another out. And that's why the puck is not jumping up in the air or shooting through the ground, or shooting through the ice, I should say. Now, we know that friction always works back in the opposite direction of the motion. So we need to decide what direction we're calling the positive direction. So in this case, I'm going to say that the puck is moving in this direction, and I'm also going to call that the positive direction. And that just gives me a map that I can use to draw in my additional force. So if the puck is moving to the right, that means it'll feel friction back to the left. So that's our free body diagram, and now we're essentially ready to start our solving process. We always start with givens and required. So we know that the mass of the puck is 165 grams, but remember, eventually if we use this in our calculations, it needs to be in kilograms. So if you do a little bit of a conversion, there's 1,000 grams in a kilogram, so we divide this number by 1,000, and it's 0.165 kilograms. That is the mass of the puck. We also know that fancy letter mu, and specifically I'm going to call it mu with a little k, because it's a coefficient of kinetic friction in this case. That's what the little k means. And it's 0.0060. Remember, there's no unit attached to it because it's just a unitless quantity. And in the end, we want to find acceleration. But once again, we know that if we want to find acceleration, we can't do it directly right now. We need to find net force first. And in fact, we're not even quite at the stage where we could find the net force, because we know one of our forces involves friction, and we're not actually told how much friction there is. So along the way, we'll also have to find FF, the force of friction. And notice I didn't even put a vector arrow on that FF, because the direction of the force of friction is not even something we need to calculate. We just need to find its magnitude, so just the force itself. And then we'll be able to work with it from there. Once again, we set ourselves up with a very similar statement to the way we solved the previous example. We can always start with a statement that net force is equal to all of our relevant forces added together. So in this case, I just include them all. I've got Fg, there's force of gravity, there is also normal force, and there is also frictional force. Now again, why isn't there an applied force forwards? Why is there only friction backwards? Well, again, because we're dealing with this situation after the puck has been shot. And so after it has been shot, the puck is just sliding along. There is no applied force pushing it forwards anymore. It's only moving forwards because of its own inertia. It will continue to move forwards because of its inertia. However, there are some other forces slowing it down, specifically friction. So we don't have to draw any additional forces going forwards because the puck was already moving forwards. So we start with this statement, but we already identified the fact that gravity and normal force are equivalent but in opposite directions, so they cancel one another out. But now we also know that we have a frictional force. So again, careful with my notation. In my next step, I'm going to take away the vector arrow and just write FF. But to indicate what direction it goes in, I'm going to stick a negative sign in front of it. Because I know that whatever direction I think the friction is, it at least is going in the opposite direction to positive. So we didn't really map this out in terms of north, south, east, or west, or anything like that. But we said that one direction, the forwards direction where the puck is actually going, is the positive direction. So anything back in the other way is a negative force. So the net force will be the negative of however much frictional force there is. Now, we are not actually given how much frictional force there is. And so a quick little aside to remember is that frictional force can always be calculated by taking your mu and multiplying by normal force. We've seen that equation before. So we could take this part of the equation that is equal to friction and substitute it in place of FF. I'm just making a replacement, a substitution. So in my next statement, I can say that we have negative mu times normal force. All I've done is replace something that equals friction with the variable that was representing friction. But I can even take that one step further because we don't even know right now what the normal force is. But in this case, and this is not always true, but it's true in this case, our normal force is equal to our gravitational force, which is actually equal to mg, mass times that special acceleration due to gravity value, 9.8. And so once again, we can perform a little substitution. We can take something that we know is equal to our normal force and substitute it in place of Fn. It's substituted in place of that variable. So really what we have is a simplified expression that says that our entire net force is really just frictional force, and that can be calculated by doing the negative of mu times mass times g, times the acceleration due to gravity. And now I have things I can just sub directly into. So it's just going to be negative 0.0060 times 0.165 times 9.8 negative 0.0097. So now we just need to take this one step further and find acceleration. So now we revert back to Newton's second law to help us out, and we can make the statement, and actually I'm just going to jump straight to it now, that acceleration is F net over m, which again is just the rearranged version of the normal version of Newton's second law that we're used to. So in this case, it's negative 0.0097 newtons divided by 0.165 kilograms. Do that little division. You get negative 0.059 meters per second squared. Once again, then, you would want a final therefore statement that is essentially saying that this either has an acceleration rate of negative 0.059 meters per second squared, or you could say that it is slowing down at a rate of 0.059 meters per second squared. So really this is like 0.059 meters per second squared backwards. And so that means the thing is slowing down when you're getting a backwards or a negative acceleration. So again, the process, we draw our free body diagram, we use that to come up with an overall net force statement that can allow us to find the net force using all of the forces involved. We take that net force and put it into Newton's second law to help us find acceleration. But now we can take this one step further and use some other things we know from kinematics. So if we also know that the puck had an initial velocity of 45 meters per second, we can now figure out how far it's going to go. And I'll just do the setup of this for you and let you try and finish it off on your own. So we know now that initial velocity is 45 meters per second forwards. And we know it's going to come to a stop. And when it comes to a stop, that final velocity then would have to be 0 meters per second. We've just calculated its acceleration rate, which I'm just going to put back into its negative form because that's the way that's more useful mathematically to deal with it. We know those three things, and we're trying to find d. We're trying to find displacement. So one of our kinematics formulas is useful when you're dealing with these four variables. So I'll let you take some time to decide which one you need to use, plug in the numbers that we have, and just to double check that you've gotten the right answer, what you should get in the end is that d, the displacement, is equal to about 17,000 meters when we round it off to two significant digits, which means approximately 17 kilometers is how far the puck is going to go. So we would need a pretty long sheet of ice, maybe shooting it along the Rideau Canal or something like that. But in this theoretical question, that is the answer that you should get in the long run. So take a minute and try and calculate that yourself using the proper kinematics formula. The final example of the curling question, that one is much more difficult to discuss through a video, so we're going to save that one and talk about it in class.